Hasn't started yet.
Not started yet. Okay. All right, welcome back. The topic now for the next hour will be this very milestone paper, sort of called BERT. It introduced an architecture called BERT. It is one of the most successful architectures based on the transformer. And we're going to go into it in considerable detail. In hindsight, this was done in 2018, 2019. But in hindsight today, it seems like there's a ring of obviousness because we have all become so familiar with transformers. And yet, the way this, when it came out, it solved a whole slew of problems elegantly. Many derivative works came out of it. From BERT came Roberta. So from BERT came Roberta, from BERT came distillation led to distill BERT. It's in many adaptations. In fact, it is from BERT that we derived the sentence encoder, the S-BERT, if you remember, which we covered early on because we are in a practical journey. But I'll cover BERT today because it's foundational, even though this is more a practical course. So if you remember, the attention is all you need paper created a classic architecture for a transformer. And the classic architecture went like this. You had an encoder into which you would send a text. The cow jumped over the moon. Right? It would have its multi-head attention. It would have many layers of attention and multi-layer perceptrons and attention and a few residual links. It's a pretty sophisticated architecture. A lot happening there. You have attention heads stacked sequentially, and you have attention heads stacked in parallel, like multiple towers of attention heads. Those towers together make the multi-head. One head is one stack. So you had multi-head attention. Out came your, think of it as your attention vectors, your attention vectors that came out of it at the end of it, right? Or some vectors came out of it. Let me generalize it because if those attentions went through some feed-forward layers, etc., some hidden state came out. For each of the words here, H1, H, moon, the last word being. This you would feed directly, these hidden states or this kind of information. And it could be multiple, like for example, key and value both. Then you would feed into a decoder. Decoder you would trigger, you would give it, okay, produce the first word. It would produce something, and then you would backfeed that word, output, back into the decoder, output. So this, once you have done the encoding, this becomes your representation. Remember, we talked about representation learning. So this becomes your representation. Do we remember this, guys? Attention is all you need. This becomes your attention. This is your representation. Language representation. And that goes into the decoder. And this remains constant. But the input keeps changing because the input is not just this. Input in the beginning was just no word, just say go. And then the first word came out and that got added to the input. So it is, whatever it is, let's say that it's a translation task, right? So let's say that out came a Hindi word, right? Something like that. So that would now go here to produce the next Hindi word, right? Whatever it is, and I apologize for people. Most of you, if you're not familiar with Hindi, just assume that cow in Hindi translates to guy. So, and the next word and the next word. So you keep on producing, and in other words, next token generation. That is why decoders, and in fact, all large language models, all language models are next word generators. Yeah? So they do a very local phenomenon. they find out the best word to say next. It's a greedy approach, greedy algorithmic approach from a computer science perspective. Now, what the BERT paper asks is that, see, when words are produced, people were looking at this architecture and doing all sorts of things, right? For things. So there's a prior work. You could be using RNN, you could be using LSTMs, you could be using just the decoder part of it, which was the work GPT. So there was a slew of work. People were trying to figure out how to use this transformer. But BERT is both extremely simple and extremely elegant. It's very powerful, simple, and elegant. That's the best way to say it. What it says is that let's focus simply on the representation that comes out. This representation. Right? We got a representation. What if this representation, the language representation, is enough to do a whole family of downstream tasks, like classification or telling whether first statement and the second statement, if first is a question, if second is the correct answer to the, is a plausible answer to the question. These are natural language processing tasks, or telling if there is a named entity here, what named entity recognition. Named entities are a person, place, thing, a person, place, organization, etc. Right? So, for example, Fremont is a named entity in the language of, in the vocabulary of natural language processing. You would say that. So you can do a lot of downstream tasks. You can do sentiment analysis, classification, a lot of these things. Could we just do that? But that begs the question, okay, how in the world are we going to train this transformer network? Now, remember, we are now acclimatized to a terminology which we talked about in the morning. We have a transfer learning. Like the best way to do downstream tasks is to follow the methodology of transfer learning, which has two principal steps. What are those two steps? Pre-training and fine-tuning. Right? So we need a transfer learning. Learning is a pre-train a model, then fine-tune to specific tasks.
Do you need to do just the encoder part? Do you need a GPU?
To do encoder part, do you need a GPU? The simple answer in machine learning is to breathe, you need GPU in this. It's like without GPU, you can't do anything. All you'll do is get frustrated. You need GPU or something that supports sort of a vector operations, vector computing engines. So, for example, nowadays, a lot of, for example, Intel is now coming out with a new batch of processors that has some matrix multiplication ability. Apple's metal chip, they call it the neural engine. That's a very nice buzzword. It contains some neural cores, and a lot of people are getting away with that. So your mileage would vary. If you were to ask for my recommendation, if I were to say, what do? I prefer working on a machine with 4 GPUs. It just takes the stress away. Like I don't continually keep hitting out of memory errors, because after a little while, you get so tired of out of memory errors, right? Out of GPU memory errors that it's just not funny anymore, right? You may be running a task for like 11 hours and then it fails. Imagine how you feel, right? So start with 1 GPU and then think about more. Go ahead.
Sorry, just a basic question. The term transfer learning, why is it called transfer learning?
Why is it called transfer learning? Very good question. So again, I'll just recap. When you pre-train a model, it is pre-trained for like a task, which is a subtext to all tasks, or a prerequisite to all tasks. For example, whether I'm doing sentiment analysis, or whether I'm doing question answer, whether something is or doing entailment, or any of the NLP tasks, one thing that is a prerequisite in the subtext for the transformer is it's better understand the language, isn't it? And so what you do in the pre-training is you create a model with great amount of data, right? Remember, what were the qualities of pre-training? It is unsupervised, means you can't create labeled data for pre-trained because it's big data, right? And it is, in a way, you hope that it is, and the word that we use these days is foundational. Foundational means it is the precursor, or it has the potential to be used for a variety of purposes. Are we together? But then you transfer it to a particular task. Two things will happen. Let's say you do sentiment analysis. Either the foundational model, pre-trained model, is good enough because it will give you a certain level of performance, right? Or you may need a further fine-tuning, further training with your own data. So when you, so that's where the word transfer learning comes from. Because what you have done is, suppose I'm doing finance. Now, when we use the word bull and bear, right, they have entirely different meaning than in the common parlance. So what do you need to do? When you bring in a model to do, for example, sentiment analysis on the stock market news, right, you need to be very sensitive to the jargon that's peculiar to these traders, isn't it? But how will you do that? You don't want to train a model from scratch. That's prohibitively expensive. What you do is, when you take a foundational model or a pre-trained model, you're transferring the learning that it has already done to your problem. And you're just solving the last mile problem. Just a little bit of fine-tuning is all that you need to do to have a very effective model for your particular domain adaptation. And that's the word transfer learning. Okay. So again, to recap.
One question.
Yes.
On the pre-train, you said unsupervised, but
how can you do that? We'll come to that.
Okay.
Hold that thought in your mind. But remember, the qualities are unsupervised, it's big data, it's foundation, and you end up creating foundation in the sense that it can do a slew of downstream tasks, can be used for slew. It is purpose meant slew of downstream tasks. Otherwise, the foundation model is no use, right? So you expect it to be a Swiss knife. So one easy intuition to carry, foundational models are Swiss knives that need a little bit of sharpening here and there. Right?
Just a quick follow-up on that.
Yes.
So in the case of that stock market example, would the fine-tuning be with the data specific to stock market, or it has nothing to do with
specific? Data specific to stock market. So you always fine-tune with fine-tuning's quality is supervised, i.e. labeled data. For example, you have to say, you have to say XY, you say market is bearish. Then you have to say sentiment negative, right? Run on the market, there's a up or some other statement positive. You have to give a lot of labeled data to do that. Fine tuning also is usually small data because creating labeled data is extraordinarily hard. As you guys have experience, or you will run data science or AI machine learning teams, you will realize that the engineers who report to you would rather cut off their right hand than sit and properly label data. It's something they absolutely hate. Right? I'm exaggerating, of course, but see, 1 second. Engineers like to be clever. Creating label data is usually not a very clever thing to do, but it is a necessary thing. And it takes a lot of patience, grit, and hard work to put it in place. So obviously, it's expensive to create label data. And so you can create only so much label data in any domain. Yes, your question.
So now RAGs is done on top of the fine tuning.
Yeah, RAG.
Yeah.
Yeah, so you can do RAG without fine tuning. You can do RAG with fine tuned model, both, if you want to. It's up to you. Generally, when you do RAG, people don't do fine tuning much.
Oh.
But you can. In fact, it's one of the things you should do, optional things. It becomes optional.
If you don't have any private data, probably fine tune.
Yeah, if it will give you better traction. Like if you know the scope of all information, you can fine tune your model with it, especially if it is not very sensitive data. But guys, we're getting a little bit tangential. Yeah, go ahead. Let me answer.
Fine tuning means like take the same model with all the weights and again train it.
Train it further. Fine tuning simply means pretend as though. So what is fine tuning? You take a pre-trained model and you pretend as though it hasn't been trained at all. So it has some weights and bias. You don't randomize the weights and bias. Right? You just take what is given and you do the normal training loop with your data.
So you need like you need also similar compute power.
You don't need similar compute power. The reason for that is these models have been trained, right? And so long as you can load the model in memory and you have enough memory to spare for matrix multiplications and storing the gradients, you're fine. Right? Because see, one way to look at it is the big tasks are done. It's like, you produce after 17 years of effort, you have produced a high schooler. But then you want to teach that high schooler some particular topic, right? Let's say, how to take something, how to cook a particular dish. You realize that the person is very well equipped, has learned the language, has learned everything. Right? It will be a last mile problem. It will be a small class to get. So that's a mental picture you have. But this foundational models have done something enormous. They have a natural language understanding. After that, any task you want to do is small potatoes for it. It can be easily adapted or fine-tuned to those tasks. That's the intuition that you carry in your mind. So with that, you fine-tune on small data and usually smaller hardware. But small is a matter of, who you talk to. Right? What the big companies look small and say, modest hardware. Just 8 GPUs are enough to fine-tune it. Right? And for you, it's like, okay, did he say 8 GPU? That's $320,000. Okay, I need to take a second mortgage. Yeah.
The fine-tuning is more for accuracy or performance?
Fine-tune is, see, the word actually, it's speed. Performance in the traditional computer science sense, that the throughput or the amount of data going through or the latency to give an inference are completely unaffected because the weights are all there. They don't disappear or they don't shrink or grow. But accuracy or the way in machine learning, the way people use the word performance, for example, for a classifier, accuracy is a performance measure. But in the AI sense, performance increases. In a traditional computer science sense, neither the latency nor the throughput is affected. Are we together here? So this is it, guys. So now the question is, the main question that BERT asks is, if I just take the encoder and I take the hidden representation, can I not do a whole set of downstream tasks? And what are the things, and that's the main thing this paper does. But the whole question is, how in the world do you train it? If you just take an encoder, you need something. You need to create a loss function somehow, isn't it? Otherwise, how would you train it? Remember, all machine learning is first you sit down, create a loss function. Then, okay, now all is well. You can take its gradient, given the gradients, backprop the gradients, and then do a step of learning, gradient descent. Right? But the whole question is, how do you take just the encoder and do it? And the trick that it uses is this. It says, take the encoder model. And by the way, it is a choice that people make. When people make this choice, it isn't that there is a deep mathematical reason for it. Right? It is something that works. A lot of things with transformers are discovered by seeing what works. They decided that, see, whenever you have a vocabulary, there will be a token for beginning, like end of sentence or something, some special tokens, but basically you have an English vocabulary. So what they do is and BERT uses a special token called CLS, and then You know, if you look at the derivative architectures, other people use other special tokens. It doesn't mean that there's something very special about the CLS token. And then you would say the cow. You do the usual thing. What will happen? These things become embeddings. Each of the word becomes embeddings, isn't it? Then you add positional embedding. You do that. It becomes your total embedding that goes into the encoder. It will go through its attention layers, and what will pop out here? Will pop out a CLS and H the H cow. You're getting it, right? Which contains how much attention each word is paying to every other word and all of those things. So far, so good, guys. This is just a standard attention method.
Talk a little bit more about how you do the positional encoding.
See, the original paper of attention is all you need used a very interesting and clever argument based on sine waves. The reason they did that, a sine function, the reason they did that, amongst other reasons, the main principal reason is you don't want to give it 1, 2, 3, 4, 5. Because when you add that to embedding, then the later embeddings begin to grow in size, isn't it? So you want something that sort of doesn't, in absolute value, remains more or less the same, but nonetheless encodes the positional information, right? And what they found is that if you use something like a sine wave, which has a limited band, -1 to 1, and then distribution, and multiples of them, you end up with a positional vector that, roughly speaking, all the positional vectors would have the same magnitude, but they'll point in different directions, right? And you add them to this embedding. But today we don't do that. Today, what we do is something is taking the whole back propagation and learning to the extreme. Positions are just learned. It says what the position vector should be. Let it learn through training itself, right? Through back propagation and through training. So we call positional as learnable parameters, the position embedding itself. But it's sort of, I'm not going into it because it's a rabbit hole. We can dwell quite a bit of time into positional embeddings, the research papers and many things around it. Right? But just take it for granted, I mean, for the sake of this paper reading, that there is an intelligent way to position it. And you attach that position embedding.
So in my mind, so sorry to ask again, but in my mind, the position of the word in the sentence is
A vector.
The meaning will change based on where it is in the sentence.
Right.
And we need to encode the position of that word in the sentence using positional encode. That's
absolutely.
That's basically what it is. Right?
That is it. That is it. Yeah. So these two should be different, essentially. Yeah. But that's what it is. Or for example, let me create a sentence where, let me cook up a sentence on the spot. Let me write a sentence. Yes. Oh, what's wrong with this? Sorry. Okay. Yes. That to align after landing. Well, I hope nobody does that, but across the river bank and walked over to his bank withdrew all his money. That's quite a story, right? In one sentence. And then join the EIT. Right? So look at the word bank. Right? And each of the three words take on meaning based on their position, isn't it? That's why you need position encoding. It's relevant. Amongst other things, right? Otherwise, so all right, so far we are good.
Sorry, big question on the CLS. So it's an input token. What value does it take?
Oh, you can reset with just some constant value. I think this paper talks about, I've forgotten what it is, but I think you just give it, I think CLS itself becomes a learnable. I think in this paper, later on, I've seen it as a learnable, but in this, they just hardwire a value. Why don't we discover it? I've forgotten. Huh? This paper is so old that it's a little bit, you remember the big picture and things like that. We'll see.
CLS token would be each for one word or for one sentence, one token?
One CLS token per sentence for one input.
Per sentence.
Yeah.
Is it per sentence or is it per chunk?
See, so is it per sentence or per chunk? Remember, guys, that in this field, the word sentences are used in the sense that it could be a word, it could be a phrase, it could be a clause, it could be a sentence, it could be a paragraph, it could be a whole document itself, right? So a sentence and chunk, therefore, are synonymous.
So for each input, there will be a one CLS.
One CLS. That is it. So whenever an input comes, an X vector, so think of it, guys, mathematically, it is like this. You would give it an X vector. Oh, sorry, why is this behaving? Yeah, you would give it an X vector. These are your words, right? The cow, something, right? What it would do is it would just do CLS and X. That's it. Does that make sense logically? It would just prefix it with this. It's nothing mysterious about it, more than that. And now it will feed it into this encoder and the states would come out. Now, as I said, when the states come out, what are your choices? You want to, let us say that you want to feed it into a classifier. To feed it into a classifier, you would give it into a softmax. Right? This will light up. It will tell the probability that it's a sentiment is positive or sentiment is negative, right? For example, customer sentiment or overall sentiment. Or you could give it more, like, is it positive, negative, neutral, right? Or if it is an emotion detector, which emotion is it? Is it anger? Is it joy? What is it, right? So you can pick your thing, right? The subject detector, you can detect this text is talking about which subject, which topic. Any one of those tasks. But in all of those tasks, if you were to, let's take as an illustration, let's take a classification task. Let's take as downstream a classification task, which is a good one to take because it's highly generalizable. Then you have a softmax here. What does a softmax function do? Softmax takes an array of numbers, let's say -2, 5, 1, 3, 9. Right. Just as a recap, what the softmax will do is it will convert this into a histogram such that all the bars will add up to 1. So it will become this and this, maybe this. This will be tiny. This will be a little bit more. This will be a little bit more. Right? These would all be such that all of these bars, so these are the probabilities. Probability. It will convert the array into a probability. So let me just call it probability of xi. So let's say that 1, 2, 3, 4, 5. 5 elements are there. Right? They now become probability of any one value. Right? The quality is that the sum of the probabilities is equal to 1. How do you do that? It actually does it very simply. It takes each number and it does a e to the xi. Right? So xi goes to e to the xi, right? And divided by the sum of all of this, so that you normalize it so that the total is 1, because you want the answer to be between 0 and 1. Right? E to the sorry, go ahead.
So how come the negative 2 the bottom doesn't below the axis?
Oh, because what is e to the -2? When you do exponentiation, e to the minus 2 is 1 over e to the 2, which is 1 over e square, which is roughly speaking, what is e square? About, let's say, 7, right? Roughly 1 over 7, right? If in doubt, do it. Okay. So it's a positive number. It's a tiny positive number, isn't it? That is. So it has become probabilities. Now, by the way, this is the definition of softmax. Just as an aside, for those of you who are actually going to implement it, because sometimes you have to implement it, don't do it this way. This formula is correct mathematically, but you will have stability problems if you use it like that. What you should do is just because it is equivalent, x max, just subtract x max from it. Oh, by the way, this is e to the minus. Oh, no, not minus, not e to the minus, just e. So e to the x max, not e to the x. Yeah, just subtract the max from it because it will just add numerical stability to your algorithm. It's one of those little tricks people don't realize. If you're making libraries, then you have to be careful. How many of you have background in numerical computing? How many of you have background in computer science? And you have not taken a course of numerical computing in college?
I do realize you don't have any 20-year-olds here.
Okay, okay, right. It's all right. I mean, this is, forget about that. It's irrelevant to our discussion. But the bottom line is we need to give it an array of numbers. But what we have here, what do we have here? We have matrix of numbers, right? We have HCLS, which will be its own array, H the, H cow. Each of these, right, is there, and that together they form a matrix, isn't it? So how do we produce an X out of it? Just an array of numbers to feed into softmax. One way we can do is, one simple way is, we can say, okay, let me take this, right? And that also explains why, like for example, if you didn't have the CLS token, you could have argued that I'll take the first words vector, whatever the first word in the sentence is, here and whatever its attentions are, I will pick that. But would that be legitimate? That wouldn't be, because that word has special reference to, for example, the word cow. Cow jumped over the moon. Cow has special attention to moon, but that may not capture the full meaning of the sentence. Are you getting my point? Right? So you can't give preferential treatment to any one of these. So what is the best thing you can do? You can say none of the above. None of these. So if you say none of these, then how do you produce a vector? You have to stick in a dummy there. And therefore the reason for a CLS. Do you see that? How the reasoning goes. That's one way of doing it. The other alternative you could have done is, you could have averaged all the hidden states. That's called mean pooling. Right? So in different situations, people use that also. But in BERT paper, this is why you stick in a CLS token, a special dummy token. It is to say that finally I'll take the attention of none of the particular words because they have contextual meaning. I'll stick in a dummy token and hopefully it will take on the meaning of the sentence. Now is it getting intuitively clear? Right. So you do that and that's all it says. So if you look at the architecture, it's beautifully done. And I invite you guys to read the original paper. Do get into the habit of reading original papers. You should read one paper a day. After a little while, it gets fairly easy to do that. But hopefully that is one of the things you will learn from here.
So ask one very basic question. So you put X as a matrix there, right? Is it like 1 point is one number, or is it like X, you mean Xi is like one?
No, X is a vector. This X is a vector.
It's a vector for 1 point, one word, or is it like a vector?
No, I'm just giving you a general. Forget about words. If you just have an array, right? You can if you have a vector array of numbers, you can softmax it.
Okay.
Right? But you can't do it with a two-dimensional matrix. That's the main problem. So you need to go from two-dimensional to just one dimension. One easy way is just take the first row. and forget the rest of the rows.
In the HCLS, you have another bracket. Is it like each H, is it like a vector of
Each
number, or is it
vector,
like one
yeah.
number?
No. Each H again is a vector. In fact, typically in attention, what is it? 64-dimensional vector or something.
Okay.
So in this case, it depends upon which BERT variant you're using, because there are many variants now. These are typically 768 or 1024 dimensional vectors. So so let me just mention it. HI usually belongs to dimensional vector D, where D and the numbers that you see quite common is this 1024. Commonly based on whether you're dealing with BERT or whether you're dealing with Roberta or you're dealing with distal BERT or you're dealing with and so on and so on.
So in this case, the array that is for HCLS
Yeah,
is based on the dimension. If it's a 768 dimension array, there are 768 representations within that array, right?
values.
Values
Yes,
within that array.
exactly. That's what it is.
Asif,
Yeah.
still I don't get that the CLS part. So the cow jumped over the moon. That is the input sentence. We need to stick a CLS vector, which is doesn't have any connection or any relationship with the input sentence.
Right.
So is it as a user we need to kind of provide that, or this?
No, the system, the BERT architecture internally will do it. You don't have to do anything.
Oh, yeah.
Yeah, you don't have to do anything.
So
See, this is why I want to go into the practical side. When we go into the code, you'll see that the code is so elegant. And this is
so
a
you
paradox.
just give that input vector and then like the algorithm or
3
whatever.
lines of code. Right? People have simplified, especially with Hugging Face and all of this. Things have gotten simplified that a lot of people are walking around calling themselves machine learning engineers who only know how to use it. They have no idea what is inside it.
Okay, so which means that okay, whatever the vector which is going to be selected by the system or the program will have some sort of like an idea about what the sentence is.
Exactly. That's the idea. That's what happens. Now you got it. So guys, look at the pre-training, this thing. I'll zoom in. Look at this. Is this what we are talking about? They become embeddings and finally they come out as, at the end of it, they come out. But the question remains, what do we, by the way, look into the paper. I'll leave it to you to tell me or remind me, is CLS baked in or it is, okay, special token, C, and the final, the hidden state, and so the CLS token, special classification token. I think it is that token is hardwired, right? They've just hardwired a set of values. It doesn't matter so long as the value remains exactly the same always. It will move forward with that. I'm pretty sure it's just hardwired.
Yeah, my understanding of reading it was that it was actually CLS. That was the value that they used.
Right. See, I mean, yeah, it maps to a point in the dictionary, like CL. Yeah, that's right. It maps to some index, let's say hardwired index 15, and that maps to its own vector. That's it. Yeah, thanks, Ryan, for that. So there we go. We have now, this is the ID, token ID in front of it. So, yeah, in fact, it is now that I think put the token ID in between, it becomes obvious that it is a fixed, it's just like any other word. You just stick a word CLS there. Thank you. So now we go to how do you train it? The training part is missing. So what you do is to train, even though you call it unsupervised learning, there is no, for class, there is no unsupervised learning, right? So these are always supervised learning in disguise. So,
Okay.
right? So you have to create labeled data. So you look at it and say, how do I create labeled data? So here is the game you play. You say the cow jumped over the moon. What you do is, sorry, you hide this word, right? So your input output becomes, X becomes the mask jumped over the moon. And mask is again a special token with its ID and therefore its unique vector. And then this becomes your X. And what is your label? Cow. Cow is the answer.
Oh,
So you say that this machine must give the highest probability, the softmax must give the highest probability to which word? Cow, right? The vocabulary will contain, so vocab, and we have to look at what the vocab size they use. These days, it's very common to use about 250K plus 2. For example, Roberta uses 250K, right? The mass jumped over the moon, and you need to have highest probability to the cow. So if you do that, can you create a loss function? What is the loss function? It becomes a classification problem, isn't it? What is the loss function for a classification problem?
in log.
Negative log likelihood, right? Negative right? Roughly speaking, it's your, I mean, this is your classification, right? And again, in Tuesday, where we do the theory, we'll cover these things in greater detail. So now you can do your loss, you can do your gradient descent. I mean, you can do your backprop, gradient descent learning, and everything. And so you go on, how hard is it to produce data, label data now, to train this model? Extremely easy. If you have crawled the web, you have bazillions of text, isn't it? Sentences. Just take a text, mask a word here, mask a word there. And in fact, what they do is they mask 15% of the words randomly, right? And then say, okay, predict what these words say. Go ahead.
What I was trying to ask, like, so you, when you're scraping the data of the web, you just keep identifying sentences and you start creating this data.
That is right. That is it. Exactly. And so suddenly you're data rich, right? You have labeled data. And so you can train this model.
Sorry, I missed the part where, so you do this masking and then you find the probability of cow. But what does that actually get us? That part I guess.
See, what happens is you want the machine, it has a vocabulary of, let's take an example, 25,000 words. To each word, it will assign a probability. That's what softmax does. Né? Remember, we talked about softmax. What does softmax do? It will give every word a probability. What do you want to make sure? That the probability of cow is the highest, isn't it? And therefore, your penalty is the measure of surprise if it is not a cow. So suppose it says probability of cow is 0.001. You should be terribly surprised, isn't it? And negative log probability.
Yeah, I understand how you derive the probability. That part I understand. But what does that get us? So basically, when we are at that point in the sentence, we want to make sure that the next word that's getting generated, the highest probability is wrong.
Yes, exactly.
That's what we're
Yeah, so this is the input. The mask jumped over the moon. This is it. It goes into the box. What comes out? Probability of all the words, right? Let's say that the art.
Yeah, that part I get. So the only question is, what is the use of this in the sense that?
What's the use of it? I'm coming to a P, let's say Zephyr. Let's say the last word. You have probabilities of all the words. What do you need? How do the machines learn? Let's go back to the basics. Machines learn this way. From this probability, and I know that the answer was cow, this is your Y hat. This is your Y, isn't it?
Right.
By looking at the gap between Y and Y hat, label and prediction, what can you tell? You can create a loss function, which is the gap between. Yeah. If it was a cow, you know it's a cow. It should have been, probability should have been 1. Anything less than that is a measure of not yet learned, isn't it? So you create a loss function. From the loss function, what can you do? You remember learning, it comes down to each of the weights, learning by taking the previous value of the weight minus a gradient descent step, right? And so the moment you can compute this gap between Y and Y hat and feed it into an appropriate loss function and take its gradient, now you can turn the dials on your neural network, and so that next time around it makes a better prediction. So does that answer your question?
Yes.
Yeah, that's it. So remember, guys, at the end of it, right, whenever you're training a model, at the back of it, remember, your goals are, you have to connect the dots to a loss function, to its gradient, to its backprop, gradient backprops, to its step of learning, which is the gradient descent step. That is all machine learning is. Right? So long as you can, the moment you hit upon a way to manufacture your prediction and that you can feed into a loss function, you're done. After that, the learning will take place and you can go on training the machine. Right? Train the code. Go ahead.
So when you say bidirectional model, can you shed
Yeah, the
more light
reason
on
is,
that?
yeah, it's a historic word. The reason for that is bidirectional. Do you notice that? So I wouldn't pay too much attention to it. See, this can pay attention to the moon and moon can pay attention to the cow. It is not, decoders are mass models. Because suppose I have only generated the cow, the next word can only pay attention to the past, isn't it? So what happened is that prior to this, people were creating models in which they would feed in, they would ask it to generate the next word.
RNN.
RNN is a classic example. And so think about RNN, and people were doing, even with transformers, they would do a decoder based thing. So what happens with RNN? You can only look back, right? And so what people started doing is creating bidirectional RNNs. They would train in the forward direction and they would train in the reverse direction to predict. Right? That's how, and those are clumsy hacks. But see, in a way, when you just use the encoder, do you see that the bidirectionality comes pretty much a freebie? Because you feed in the entire sentence. You're feeding in the sentence, the cow jumped over the moon. Remember, in a transformer, the whole sentence goes in one shot. Bidirectionality is inherent in the encoder of a transformer, isn't it? A word can pay attention to words before it and after it. It is inherently bidirectional. In an encoder, when you feed in a sentence to the encoder part of a transformer, what happens? Every word pays attention to all the words around it, whether in the forward or the backward direction. That's how it is, right? You don't say that, no, I'm going to only look left or right. You don't say that before or after. Every word has a chance to pay attention. Remember, what was your basic equation? A K, Q, softmax times V, basically. Now, do you realize that nowhere does it say that there's direction there. Every word, so suppose you're talking about attention, query, attention I is paying attention to every word J, irrespective of whether it comes before or after. It's built in.
Within the context window.
Within the context window, yeah. Within whatever input you've had in. Yes, that's right.
So let's say, suppose if my sentence is only one word, just cow.
It will pay attention to itself.
That's it.
That's
But let's say if I'm asking what would be the next word, just give cow.
If you give cow, it will still be able to predict into it. Because what will happen is, think about it this way. The cow, just one word, and the CLS token go in. Ultimately, there is a H CLS, H cow. And then this CLS is fed into a softmax. And hopefully, it will increase the probability of the word jumped, cow jumped, potentially. From historic data, so cows do many things. Cows eat, cows graze, cows jump, right? Cows moo. Maybe probability of the word moo would be high, probability of the word graze, probability of the word eat. These would be high, or probability of the cow, of the word run. But the probability of the word automobile should be close to zero. Does that make sense?
What happens if you have the same probabilities? Cow moving and cow jumping.
Oh, if you deal with floating point numbers, you really don't have that. Right? These are high precision numbers. So one will be more than the other. But having said that, I must say that with the encoder, it may just pick one. But in the decoder today, what we do is, because we use generative tasks, the creativity of the LLM comes because we don't just pick the highest probability as the answer. We sample off the probability. But let's keep that as a topic for another day.
So the jump, move, raise, all these things are in the 250,000.
Yeah, exactly. The entire English vocabulary is there. So what happens is English vocabulary is millions of words. You keep a reserved words for other. You encounter a word you don't see in your vocabulary, you give it the token other.
So that is the beginning state.
Yeah, that's a beginning state. So your vocabulary contains, therefore, the word CLS, a separator.
Mhm.
These are special tokens, separator between sentences,
Marks.
end of sentence, EOS, things like that. And then it contains the actual work, like artwork, all the way to last word.
Yes,
I don't know. Z, Y, maybe zygote.
Okay.
And to each of them, you just have an index, whatever, some index is there, number is there. And then, therefore, from there onwards, it's a simple thing to look up its vector embedding. Or learn its vector embedding, better still. Right, so this is it. This is, guys, are we getting it? And this is the whole process. You take the position embedding, and now the one subtlety with BERT is you don't feed it. It takes 2 sentences as input. It was trained with 2 sentences as the input. The reason? And so,
questions going back on that mask.
yeah.
How many masks do you have in a sentence? Just one mask, or
You take 15% of the words, you mask it, and you ask what was the first mask, what was the second mask, and so on and so forth. But roughly speaking, for understanding, right, just imagine one word is masked, right? Because then it aligns with intuition very easily. But see, with all of this, now there are computational and mathematical subtleties all over the place. So ignore that. So what happens is that there is a separator between the words. There is a CLS token. There is a padding token. Oh yeah, padding. Padding is what? If your sentence finishes here, pad. Right? It will put it here. Now, one of the interesting things, because you fed it in pairs, they deliberately did that because they were thinking about things like alignment between 2 sentences. Like, for example, question answer. Is the second question the answer to the first one? Right? Or is it an entailment? Like, does it logically continue the thought? Things like that. You could use it for a lot of downstream tasks. For classification, you don't need it. Suppose you want to, given a text, you want to classify it as positive, negative, or some sentiment, neutral sentiment. You don't need the second sentence. So what do? How do we feed that in? To a machine that expects 2 sentences.
Pad.
So leave the second one, pad it. Leave it as empty. Right? That's that. So that's that. So those are the things. So what it needs is every token, therefore, has 3 things associated with it to define it. It needs a position within the sentence. It needs which of the 2 sentences it belongs to, first or the second. And it needs, of course, the word embedding. Right? So position embedding, segment embedding, and token embedding to make the total input embedding. Are we together now, guys? Is it simple? So that was BERT. And if there are no more questions, I'll stop here. Questions.
Asif, I just had a question on the positional embedding. I once read this paper and I had the impression that it also takes into the account the position of a word in a sentence, and then what is the position of a sentence in the paragraph. Is that true?
No. No. See, the thing is that a sentence and paragraph in NLP, right? Yeah. There is no distinction. You feed it a paragraph, it is a sentence. So the only thing it will care for is what is its position in the paragraph.
But
because full stop, right, is for it. Full stop is just another token. It doesn't recognize it.
But when you have this next sentence prediction, in that case, the next sentence is masked as compared to the training data is such that
You
the next
don't
sentence
do
is
next
masked.
sentence prediction.
I think
You do a next word. All you do is you say, is the next sentence, is it,
because in the training paragraph,
which page?
the heading, pre-training where you do it.
Yes. Yeah.
On the
So
page
what they're talking about is to
the next
ask this
sentence-
question, your NSP. Let's read what NSP says, then it will clarify for you.
Yeah.
Many important downstream tasks, such as question answering and natural language inference, are based on understanding the relationship between two sentences, right? Which is not directly captured by language modeling. Language modeling is mass language model, right? In order to train a model that understands sentence relationships, we train for a binarized next sentence prediction task that can be trivially generated from any monolingual corpus. Specifically, when choosing the sentence A and B for each pre-training example, 50% of the time B is the actual next sentence that follows A, and 50% of the time it's a random next sentence from the corpus. So you feed it a genuine next sentence and you feed it or random. But what are you predicting? You're not predicting the next sentence. You're predicting whether B, the sentence B, genuinely follows sentence A, or is it a random sentence? It's a binary prediction, right? Are we understanding it? A prediction is a probability. Probability of what? Is B really after A or it is not? That's all it can predict. You got that?
Yeah.
All of what we are talking is part of the pre-training, right? Training the model
Yeah.
before it becomes available as a model that others can use.
Download it, right? Yeah, that's right. And so, guys, there are very interesting things. This model was trained on two separate tasks, both fill in the blanks, and so that will have its loss function again, the negative log likelihood, but based on which word was lost. Then the other task that is there is the next sentence prediction, which says, okay, I give you two sentences. Does the second sentence follow the first or not? Is it random? Right? So you come up with the probability of that, and it will have its own log likelihood. But these guys thought, of course, it's a good idea to make it more robust by training it on two different tasks. Right? Also, both of them are free to create. How do you create that? You take a sentence. I mean, when you create the training data, you just take a sentence, the next sentence prediction. You take a sentence S1 and you take literally the next sentence in the text S2 and you create the probability 1. Then you take another S1 and you take a S random and you give it a label 0 and you train it on that. Right? Easy to train the machine onto that. Later, this topic in subsequent papers got revisited. For example, in the Roberta paper, which took the idea of BERT forward quite a bit. Right? It fine-tuned the machine. I mean, it sort of did a lot of hyperparameter tuning and a careful look at BERT and improved upon it. One of the realizations that they had is that forget the NSP, just train it on one task. Right? And you get sort of improvement if you just focus on training it on one task. But that came later, in a separate research paper. So guys, at this particular moment, now what happens is that when you trained it on that, or whether you can have a question answer, whether this answers this question or not. Many tasks, when they looked at the benchmarks, and this is where the thing got interesting, they realized that you have trained just the encoder using or pre-trained it. Right off the bat, you were achieving state-of-the-art results. So BERT became foundational model that led to a lot of improvements and variants and things like that. Roberta, for example, is a variant of it. DeBerta is a variant of it. When you distillate it, then what is distillation? Distillation is the process of reducing something to its essence, right? For example, you take salt water and you boil it, take the steam and condense it, you have a distillation. Right? So in the same way, in machine learning, when you have a huge, big, complicated model, there is a process of training called student-teacher loss function, by which you can tell the student that learn only the essential features that the teacher has learned. Forget, don't have to learn all the details. We'll cover distillation at some point, but not now. Right? So you can distillate. So you get a much smaller model, a student model, that is almost as good as the master. So distillation scheme. So BERT became foundational to many, many derivative models after that. And in fact, the paper that I was going to do, the VIT paper, if we go back and revisit the VIT paper, let's go back and do that. Let's revisit it and see if it makes more sense. So what are we doing? We are taking patches of the image, just flattening it out into a single vector, right? That is the same as word embeddings, right? Add position embeddings and then feed it into BERT. Does it look like BERT to you now? Look at it, right? You have a special token. Feed it into BERT, and what do you get? You get. Now, in this particular case, I will, they have used, yeah. So you do that, you feed the result out and feed it into, what is MLP head? 1 second. What do you think is the MLP head? Multi-layer perceptron, right? So I remember feed forward networks. You take it, you pass it through a few more distortions, and then also, and then you feed it into the softmax classifier, right? To tell whether it was a bird, a ball, a car, or whatever it is, your question.
So the question in a sentence, right? When you go position 1, 2, 3, 4, 5, it's linear. Here, right, I could go 1, 2, 3, 4, 5, 6, or I could go 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? Does it matter or?
Yeah. See, the beautiful thing is positions are learned. So let it learn on its own the best way of figuring out the position encoding. Right? That's the best part, because your thought is absolutely valid. I can go like snake-like, I can go up like this. In a two-dimensional, there are many ways of going about it, right? Or if you come from the Middle East, you would go this.
Correct. Right? Even language, right? You know, left to right versus right to left.
That's right. That's right. So I remember I once read some British book, old British book, and the author was describing languages of India. After a little while, the person got carried away, and he said, in India, some languages go left to right, some go right to left, some go from top to bottom, and some go from bottom to top. So it's like that. In visual, you have to think.
There's one thing here, like for the time formula architecture for BERT, there's a finite vocabulary, but this is not an infinite vocabulary.
That's the best part, because see, you need a vocabulary to create an embedding, indexing. But here you don't need any of that, because the pixel value itself is the embedding. You see that, right?
Yeah.
Just the pixel RGB values, the value is the embedding. So let's take a little patch. Let's illustrate this with a little patch. See, if I take a little patch, 16 by 16 patch, cross 16, right? That will be made up of 3 channels, 16, 16 red, green, RG, green, B, blue. This is also 16, 16, right? It is there. Now what happens is each of these, sorry, I need to do this and turn off the touch. Okay, so each of these, in each of these channels is just a number, isn't it? Yeah. And so what can you do? Just read it like this. In this particular case, read the first row, then read the second row, the third row, fourth row, and keep concatenating it to a single one-dimensional array, and then go to the next one, do this, keep doing this, and then go to this, keep doing it. And then you'll get one giant long vector, and you call it a word embedding, or rather a patch embedding. That's it. Right? So you don't need, the beautiful thing is, you don't need a finite vocabulary.
So here also you are doing next sentence prediction, next patch prediction?
No, there is no such thing. You don't do that.
Every patch is getting followed by another patch, you see.
Yes. See, Shweta, that was the original BERT paper. Here, there is no need for it. Now, think about it this way. Look at this. What are you going? You have the equivalent of a special token. CLS token. It's giving you a vector. You can feed that into a softmax to tell what is it, cow, bird, etc. Right? All you need is label data, which is what? A picture. And this is your X. And what is your Y? Label called cat. That is it. There is no such thing as next sentence prediction. I mean, that construct doesn't make sense.
Yeah, but, in traditional CNN, where you have computer vision, this thing works that you have a picture and you have a label. But here you're dividing the entire image into 6 different patches. And then
6, no. Oh, you mean 9? Yeah,
Yeah.
in this little picture, it seems to be 9 different patches. Yes.
It divides the image into fixed size patches.
Mhm.
And now when you bring those patches together, there has to be an algorithm behind it that it needs to bring them in together.
Oh, but no, I don't understand about bring it together. For what possible purpose? In this paper, that there is no such purpose to bring them together.
No, my point is like initial image was divided into patches.
You decomposed it into patches.
Yeah.
So let's go through the process.
Yeah.
From the patches, you create a patch embedding.
Yeah.
Therefore, that each patch acts as a word.
Yeah.
Therefore, I have a sentence.
Yeah.
Do I have a sentence or not from a picture? A picture has become a sentence, right?
Yeah.
Right? Each patch is the word. If it is a sentence, I can feed it into BERT.
Yeah.
Yes, I can. Therefore, for the special token, I can get a hidden state vector.
Yeah, we can.
That I can therefore use for classification of what animal, what is it that I saw in the picture. That's it. That is it. That is what this paper does. All that. And did you follow that? Like, is it making sense? Right? That is all that this paper does.
Encoding it here, we're not decoding it.
You're not decoding
That's
it.
so
There is
if we
nowhere a
decode it,
decoder.
Then you will have these positional things there. We're just encoding it and putting it,
Yes, yes. Remember, what did we say in the BERT paper? Only the encoder, right? And as this paper, as this clearly, so look here, this is transformer encoder. You're only encoding, right? That is it. That is it. Your question.
I'll go back to my earlier question. The follow-up is like, the cow jumped over the moon. There is a sequence, right? But if I'd written that sentence as cow, moon, jumped over the, or something like that, the positions are now different.
Yes.
And that problem I see in how I go. And you answered me saying, let the machine figure out the position.
Yes, and it is very smart at figuring out position patterns.
Okay.
Right. So see, even today, right, almost for text also, almost all modern transformers leave it to the machine to learn the position. Always. And it finds a clever way to do that. Yeah, that's why they're called learnable position embeddings.
So technically, then it really doesn't matter the sequence in which we are reading.
Yeah, it doesn't. So long as it is a sensible sequence. That's when it does the right thing. Are we together, guys? Let's see what your main concern is. Like, we play this puzzle, right? A picture puzzle, and you can move things around, like 16 by 16, except that there's only 15 pieces. So one empty slot and you can move things around. It isn't like that. You basically say, here's a picture, and I'm going to give you picture after picture. How would you remember the position of each patch? Find a good way to remember the position. It learns it. Right? It just learns it. So guys, is this paper, now VIT paper, is it looking straightforward? It's a very direct application of BERT. The key insight is to convert an image into a sentence, yeah, by taking patches of it as words. That's a key insight. And with that key insight, you move forward. Right? It really opened the door to a lot of things. In fact, it was pretty revolutionary actually, this paper. Yeah. Immediately, the reaction was immediate. A whole floodgate of papers began to come out, applying transformers to computer vision and natural language, visual language understanding.
To understand correctly, like you show like thousands of images of cat, each image is being split up, each image piece is getting a vector,
Yeah.
And then after like all the learnings, you give one image, is this a cat or not?
Yes. Yeah, that is it. And it will answer it correctly.
Because of
Yeah.
embeddings and everything, it just
Yeah.
compares embeddings.
Right.
Gives output.
Yeah. And see, guys, these days, right, most of these transformers, their accuracies are very high. On public data sets, they're very high because they've been trained and trained and trained, or rather pre-trained is the word you would use. So once it has done that, you can, of course, choose to adapt it to different tasks or fine tune it if you want to. I'm giving you the task, go fine tune it and make it work for pepper trees and weeping willows. Okay, any more questions before I end the recording? Anybody remotely would like to ask a question? Is it clear, guys? Was it easy to understand? Bhavin.
Basic question on the decoding parts, like how
There is no decoder here, so let's not bring it up.
so
There is no decoder here.
it just classifies.
Yeah, it's just the encoder. Remember, I started by saying BERT uses only the encoder, not the transformer. Yes.
Ask a dumb question.
No questions are done. Go ahead.
Keep referring to this word foundational model. And a lot of things we refer as foundational model.
See, the rule is very, what is a foundation model? If I made it, it's foundation. If you made it, it's irrelevant. No, more. So the qualities of a foundational model is, it has been trained. Generally, these are pre-trained models, where the people who created those models had an eye to solving a whole class of problems, not just one problem. And that can be fine-tuned to further train to do even better if needed. Right? So such models are called foundational models. I believe the first person to use the word foundational model was Fei Li at Stanford, the professor at Stanford University. I think she and her group coined the term foundational model. I may be wrong, but check it out.
There are a lot of foundational models. Is it?
There are a lot of foundational models, yes, not too many though. See, on Hugging Faces, you find already more than 500,000 models posted. But you can count more, like most of the foundational models, I think I know about 80–90% of them, and there's a much smaller set. So, good. Any more questions?
So is ChatGPT a foundational model or?
The ChatGPT is an application. Behind it is a very complicated architecture, and there are a mixture of experts, and there are many, many things happening. And we will get there, guys. See, by now you must have realized that we are just 4 weeks in to LLM, and this topic is vast. This zoo, it's like the San Diego Zoo, right? You can't just visit all of it in an hour. We have a lot of things, a lot of exotic beasts to meet. We are just beginning to scratch the surface of this. So guys, if nothing else,